Okay, so welcome back. We are reviewing the Ahmad Ibrahim Secondary School paper. So just ensure that you have the paper in front of you. As per yesterday, we will not be going through every single question, just selected questions to ensure that we know the concepts. Okay? So just give me a minute while I start. Okay, so I won't be going through every single question in the Ahmad Ibrahim paper, but I want to go through some in greater detail than others. Now, in question 1, these are the 5 steps of the blast furnace. You need to be able to write these equations from memory, okay, as part of the section B essay or as part of any question asked of you. Just like salt prep, blast furnace is the last year in the syllabus. So it's a good idea to be studying it in great detail. So you realize these are the 5 reactions. Okay, you need to know what the 5 reactions are. You need to know what kinds of reactions these are as well. So the answers are as follows. All right. Which equation shows combustion? That's A. Now, how do you know that A is combustion? Now, combustion is a reaction whereby it reacts with oxygen gas. So you should have plus O2 in the equation. Okay, so how do you recognize combustion? You recognize combustion when you see plus O2 on the left-hand side of the equation. Okay, next, D is thermal decomposition because D shows the decomposition of limestone to calcium oxide. Okay, so limestone decomposes when heated to form calcium oxide. So that's D. Next, which equation shows the formation of a toxic gas? So in this case, the toxic gas being carbon monoxide, and therefore it's B. Okay, and finally, D and E have the same answer. That's equation E. You need to know that equation E involves an acidic oxide and a basic oxide. So it's a reaction between an acidic oxide and a basic oxide. That's E. All right. And this is also a reaction whereby impurities, namely the acidic SiO2, is being removed from the blast furnace. Okay. Now, I think I've mentioned to you this many times. A to C, they are redox reactions. D and E are not redox reactions. Okay? Next, equation C is the equation for obtaining iron. So if they will ask you, write an equation to show how iron can be obtained in the blast furnace. If they just ask you to write one equation, which equation would you write to show that iron can be obtained? All right. So the equation should be, okay, just give me a minute. The equation should be C. Okay. So you will write equation C when you are asked to write the equation to show how iron can be obtained. Okay. So just please ensure you take these details down so that you are fully aware of it. All right, next thing you should take down now. I think yesterday we went through what are the waste gases from the blast furnace. There are 3 main waste gases from the blast furnace. 2 of them are carbon monoxide and carbon dioxide. However, the most important, the primary waste gas from the blast furnace is actually nitrogen. Nitrogen comes from the air and it's unreactive. So yesterday we went through this during the lesson. Nitrogen is the major component of air. And because air is blown into the blast furnace, okay, nitrogen is therefore present as a waste gas in the blast furnace. Moreover, nitrogen is unreactive due to the strong nitrogen-nitrogen triple bond. Therefore, nitrogen will not take part in any of the reactions in the blast furnace. So nitrogen will just enter and leave from the top of the blast furnace. Okay, so these are the 3 main waste gases in the blast furnace that you must be aware of. Now next, you are asked why steel is preferred to iron. So I'm sure you know the answer. Steel is stronger and harder than pure iron itself. And this is because steel contains iron and carbon atoms, which have different sizes and therefore disrupts the regular layered arrangement of the atoms. Hence, the layers cannot slide over one another easily when a force is applied. Now, in this question, to make your answer better, please try to state the specific atoms present in the alloy. This is not a general question. They are asking you about steel. So it leaves a better impression if you can state that steel contains iron and carbon atoms. Okay, steel is only iron and carbon. Now, for your syllabus, you don't need to know how steel is actually made. All right, you don't have to know how steel is actually made. Okay, but steel is made from iron. However, since we have a little bit of time as we go through the paper, let's talk about how steel is made. Now, steel is made obviously by adding carbon to iron. So carbon is added slowly to molten iron. Now, the slowly is important. You don't want to be adding too much carbon to iron. Now, why is it important to control the amount of carbon you add? This is because too much carbon in the steel makes it brittle. So if you add too much carbon, the steel becomes very brittle. Brittle means it breaks easily. All right, so you need to add the carbon slowly in a controlled manner to the molten iron from the blast furnace. And this process, the addition of carbon to molten iron, takes place in an argon atmosphere. Okay, so carbon is added slowly to molten iron to make steel, and this must take place in the presence of argon gas, argon atmosphere. Why argon? What's the purpose of argon here? So you have learned about argon, right? Argon is an example of what kind of elements? Argon is a noble gas in group 0. So what do we know about noble gases? Noble gases are all inert and unreactive. So argon provides an inert, unreactive environment. Why is it important to provide the inert environment for this process? The inert environment helps to prevent iron from reacting with oxygen. If you just did this process in the air, the iron can react with oxygen to form iron oxides. So it is important when you make steel to carry it out in an argon atmosphere. Okay, so please ensure you take this down so that you are aware of how steel is made and why the carbon must be added in a controlled, slow manner. Because too much carbon will make it too brittle. Okay, so now that we know how steel is made, something else about the blast furnace. So you can see blast furnace, we have talked about many things. We have talked about redox, talked about waste gases, talked about how steel is made. All right, something else about the blast furnace that you should be aware of is it is important to ensure the raw materials are dry. So if when we add in the hematite or when we add in the coal or the limestone, it is important to ensure the raw materials are dry. Why? Why is it that the raw materials cannot be, say, wet? If it's wet, the H2O will form steam. The steam reacts with molten iron. All right. So can you imagine if the raw materials are wet, there is steam. The steam then reacts with molten iron. Now, this may not seem like a bad thing, right? However, if the steam reacts with molten iron, it will decrease the yield of the iron. Means how much iron you get will decrease because the iron is formed and then it reacts with steam. So it doesn't stay as iron. And besides that, it forms hydrogen gas. So if you recall, under metals we learned, right? Iron metal reacts with steam slowly to form iron tetroxide and hydrogen. So the process forms hydrogen gas. And hydrogen gas is explosive. So this is very important. If the raw materials are not dry, then you have steam formed. If you have steam formed, then it might form hydrogen gas when it reacts with iron, which of course might cause an explosion in the blast furnace. Okay? Now, once you're finished copying this out, please give me a thumbs up so that I know you're done. Okay, now we move on to question 2. Now, question 2, I'll just run the answer through very quickly. Now, figure 2.1 shows the ion of element R. You can see that there are a few pieces of information. Number 1, element R forms a 2+ ion. So immediately you must see 2+ means what? It means in terms of electrons, the atom lost 2 valence electrons. Okay, and that's how it forms a 2+ ion. Okay, 2+ charge occurs because the atom lost 2 valence electrons, as I've said there. Now, the atom lost 2 valence electrons. That is how. This answers how. But where is the why? What's the reason for it to lose 2 valence electrons? It loses 2 valence electrons so that it achieves a fully filled outermost electron shell. This is the why. All right, so just to take note, you must answer both aspects of the question. Now, once you have established that it lost 2 valence electrons, it has a fully filled outermost shell now, then drawing the dot and cross diagram should be relatively straightforward, given that you also know that oxygen atoms gain 2 valence electrons. All right, so obviously the oxygen atom doesn't stay as an atom. It needs to gain 2 valence electrons from R so that it achieves a fully filled outermost electron shell as well. All right, moving on. Figure 2.2 shows you a cluster of simple molecular compounds. Simple molecular are things like H2O, right? So you're asked to name the forces X and Y. So X is a weak intermolecular force of attraction and Y is a strong covalent bond. All right, so this one you must be very aware. You see that force X is between molecules. That's why it's called intermolecular. Intermolecular means between molecules. So these are molecules. Okay, so you must recognize weak intermolecular forces of attraction. They are between the molecules. The strong covalent bonds are inside the molecule. Okay, and finally, what's one physical property? Low melting and boiling points. All right. All right, so we were on question 2. Now it's important to recognize simple molecular structures and where the intermolecular forces of attraction are and where the strong covalent bonds are. Okay, now I've mentioned so far that the exam is moving towards a more conceptual kind of question. So one concept they haven't really tested the students is the concept of covalent bonding. I hope you know by now, simple molecular structures, they have covalent bonds. The covalent bonds are inside each molecule. It is just that in between the molecules is weak intermolecular forces of attraction. Next, in a simple molecular structure like this one, we will say that the molecules are small and discrete. Okay? Now, I believe the word small, you probably understand it. Small just means that it doesn't have a lot of atoms. Okay? So like H2O is a small molecule, CO2 is a small molecule, O2, small molecule, HCl, also small molecule, right? But the word discrete may not be a word that you fully understand. So when it was taught to you last year, what does discrete mean? Now, discrete means it has a defined chemical formula. Another way to put it is the molecule has a boundary. You know where the molecule ends. Take, for example, H2O. H2O, you know that the molecule is 2 hydrogen, 1 oxygen. Okay? If you have a chemical formula for the covalent compound, that means it's a discrete molecule. Now, this is particularly important because many students seem to think that polyethylene is not simple molecular. If you recall when we learned polymers, we drew polyethylene like this. Polymers are drawn like this, right? This is the structure of polyethylene. However, just by drawing it like this, does it mean it's no longer simple molecular? No. Polyethylene is still simple molecular. But many students will argue, oh, but polyethylene is not small, right? It's a large polymer, right? Exactly. It's a large polymer. However, it still has discrete polymer chains. That means there's still a boundary as to how long the chain is. All right? How do I know there's a boundary? There's a defined length. The discreteness of the polymer chain comes from the number of repeat units. We know how many repeat units there are in a polymer. So like polyethylene, we know it has 1,000 repeat units or 500 repeat units. The value of the repeat units is defined. Therefore, we still say that it's a discrete molecule. And hence, polyethylene is still simple molecular. Okay? So let's just take that down to ensure that we get the concept right. Okay, moving on. So explaining why simple molecular compounds do not conduct electricity, I think that's quite easy because there are no free-moving ions or electrons. Please don't forget ions or electrons must be together in your answer. Okay, now I want to spend more time on question 3. Now question 3 is not difficult. Question 3 is about how pH changes as you add sodium hydroxide slowly to the mixture. All right, so what are you adding? First, you start off with 20 cm cube or 0.05 moles per dm cube HCl. All right, this is acidic hydrochloric acid. You are titrating it against sodium hydroxide to produce sodium chloride solution. So you are measuring the pH using a pH meter. So pH meter is a very useful instrument to help you measure pH. All right, so this is quite a useful instrument to remember. Okay, if you recall, we spoke about this as we went through the year 2020 TYS. Okay, in 2020 TYS, you have to plan an experiment to figure out which alcohol is more quickly oxidized. So how do you measure the oxidation of alcohols? Alcohols are oxidized to form carboxylic acids. So you measure the pH of the mixture as time goes by. That will tell you how the alcohol is quickly or slowly oxidized. Okay, but over here, this is not about speed of reaction. This is about titration. So you can see, this is a typical titration curve. It's called a titration curve because it shows you the change in pH with the volume of alkali added. So what is the original pH of the acid? The original pH of the acid is 1. So in this case, the original pH is 1. Okay? Now, It starts off as pH 1 because obviously HCl is strongly acidic. Okay, so before adding NaOH, it's just HCl. HCl is strongly acidic. Then the pH starts to increase gradually. But there comes a point whereby the pH literally shoots up immediately, right? This vertical increase in pH tells you that pH is increasing drastically at that particular drop, that particular volume of sodium hydroxide. And this is called the end point of the titration. The end point of the titration tells you where complete neutralization takes place. How do I know that this is complete neutralization? We can think in terms of the pH. At first, it's hydrochloric acid, is acidic. But as you add sodium hydroxide in, it becomes less and less and less acidic. And up to a certain point, there is only one tiny drop of acid left. That tiny drop of acid reacts with one more drop of NaOH, and all the acid is suddenly gone. If all the acid is suddenly gone, the pH will no longer be less than 7. Because we know that acids have pH less than 7. So if there's no more acid left, the acid has completely gone, then the pH will have to increase suddenly and drastically upwards to above 7. Okay? And this is the vertical region that you see highlighted in yellow. All right? Now, to work out what is the volume of NaOH needed for neutralization, we basically work out where is this massive rise in pH. We trace this massive rise in pH down to the x-axis. So this is what I'm doing now. You can see me doing this. We trace it down and we realize that it's 30 cm³ of NaOH. Okay, so 30 cm³ of NaOH is needed in order to neutralize the HCl solution that you have. Okay, so I believe you know HCl and NaOH, this is neutralization. The ionic equation, now importantly, please read, it's ionic equation. The ionic equation is just H plus OH minus forms H2O. Okay, so this works no matter which acid or which alkali it is. It could have been sulfuric acid and sodium hydroxide. The ionic equation will still be the same. Okay, so it's good to memorize the ionic equation in part B. And then in part C, you're asked to deduce the volume of NaOH. The volume of NaOH is, of course, 30 cm³. Okay, so over here, I've chosen to give it to 1 dP, okay, following the question. Now, in part 2, you're asked to work out the concentration of sodium hydroxide. So how do you work out the concentration of sodium hydroxide? This is where it's very important to pay attention to the numbers which you have underlined. So if you have underlined the numbers in the question, you will know that you have been given the volume of HCl and the concentration of HCl. This will allow you to find number of moles of HCl. We can find number of moles by using the formula NCV, where N is equals to C times V. 0.05 times 20 cm³. Please ensure that you actually divide by 1000 to convert the dm³. Okay, so once you have found number of moles of HCl, then it's 1:1 mole ratio. And then the concentration of NaOH is just 0.0333 moles per dm³. Okay, to 3 SF. Clear? Now I'm going to ask a separate question from this. So you have already calculated concentration of sodium hydroxide, but how about calculating the concentration of NaCl at the end point? What is the concentration of the salt, sodium chloride, at the end point of the titration? Okay, so I shall pause the recording. Please think about it and work about it. Okay, the answer for this question is actually 0.02 moles per dm3. Now, there's a massive trick how we got 0.02. I'm sure all of us know the formula triangle now. NCV. In order to get concentration, we will need number of moles. We will also need volume. So first, we have to first calculate what is the number of moles of NaCl. But this is relatively easy to do. We know the mole ratio between HCl and NaCl is 1:1. And we already know how many moles of HCl we have. The number of moles of HCl is 0.001, right? This came from the previous part that we did. We worked out that the number of moles of HCl is 0.001. And therefore, NaCl is also 0.001 moles. Okay, so this part should be relatively straightforward, finding number of moles of NaCl. The next part is where the trick comes in. The concentration of NaCl at the endpoint is the number of moles over volume. The number of moles is 0.001. However, the trick lies in the volume. Now, what is the volume of solution at the endpoint? Some students may think, oh, the volume of solution is 30 cm3 because I added 30 cm3 of NaOH. Some students will say, oh no, the volume of solution is 20 cm3. I put 20 cm3 of acid into the flask, what? But the answer is neither. What is the total volume of the solution in the flask at the endpoint? If you think about it, at the endpoint means what? Just now we said about the endpoint, right? Endpoint is when neutralization has taken place. Endpoint means I've added 30 cm3 of NaOH. I added 30 cm3 of NaOH to what? I added it to 20 cm3 of acid, meaning the total volume now, HCl plus NaOH, the total volume will be 20 HCl, 30 NaOH. So the total volume is actually 50. So this is where the trick lies. You need to know the total volume is now 50. You need to remember to add the acid and the alkali volume together in order to find the concentration of the salt at the end point. And once you do this, I'm sure you get the answer. Okay? So this is the massive trick. Okay? Now you may be wondering, why do we do this trick to find the concentration of the salt at the end point, but not to find the concentration of NaOH? This is because when you're asked to find concentration of NaOH, we mean the concentration of the NaOH in the burette, the original NaOH. But the NaCl is different. The NaCl is a product formed in the flask at the end. And the flask volume is not 30 or 20. It's 20 plus 30 equals to 50. So this is the major difference between how we do the calculations for NaOH, which is an original solution, and NaCl, which is a product at the endpoint. So please ensure you take this down and know the trick. Okay, moving on. Part D. Okay, what is the color of the universal indicator when 40 cm3 of NaOH is added? Now, 40 cm3 is clearly more than 30. You only needed 30 cm3 for neutralization. So by adding 40 cm3, now we have excess NaOH. If it's excess NaOH, it means that it's going to be, the final solution is going to be alkaline. And that's why you see the color changes from red, then to green at the end point, then to purple at the very, very end when 40 cm3 has been added. So you must have all three colors from red to green, then to purple. Okay, can? Now I'll skip part E because part E, you can actually do it yourself. I'll just read the answers that come with it. I think you're already very familiar with part E. All right. So moving on to the next question. Now, next question is about chromatography. I think most of you should be already very familiar with how to do chromatography. Okay, so I shan't harp on it. But let me just explain part C once more. So it is very important during chromatography to ensure that the solvent level is below the start line. Meaning, if you dip the paper into the solvent, that solvent should be little solvent, so that the solvent level is below the start line. And this is to avoid the dyes from dissolving directly into the solvent without moving up. Okay, so that's for part C. Now, let's go through part D together. Besides chromatography, describe briefly a test to check if the food dye sample is pure. All right. Now, what can you do to check whether the food dye sample is pure or not? Now, in this case, the food dye, you are not told if it's a solid or a liquid. Most food dyes tend to be solids. So if it's a solid, we can measure the melting point. So whenever you're asked to determine the purity of something, we should measure its melting point or boiling point. So in this case, I'm assuming the food dye was originally a solid, okay? So you can measure the melting point of the food dye. But don't stop here, it's 2 marks. Always look at the mark allocation before you decide how much to write. So if the food dye is pure, it will have a fixed melting point. Okay? How about if it's impure? So you must write both sides of the story. You cannot just write one side. If it is impure, it will melt over a range of temperatures. So if you have written boiling point instead of melting point, I think that's okay for this question because you are not told if the food dye is a liquid or solid. Okay, but please ensure that you have the 2 sides of the story. If it's pure, what is it? If it's impure, what is it? You must have both. Okay? So I don't know how the answer phrased, but it's important to phrase it like this. Okay? And once more, may I stress to you, please don't write things like, it has a range of melting points. That's wrong. Write this instead. It will melt over a range of temperatures. So it's not the same meaning. Okay, so moving on from the chromatography. The next question, I think, is relatively straightforward. It's QA. I think most of you would have gotten the 5 or 6 correct. Now, can I just stress one thing though? When you're asked for the ion, you must put the 2 after the ion. So F2 plus is iron 2 ion. All right. You could also have written the formula Fe2 plus, that's also fine. But if you want to spell it out, please ensure you write iron 2 ion. When do we not write the 2? We don't write the 2 when it's a metal. If it's an element, there is no 2 on it. Okay? So you must know the difference between the ion, which is part of a compound, where it has the 2, and the element, the metal on its own, will not have a 2 on it. Okay? So I believe this QA is relatively straightforward. I think most of you will be able to quickly work out, okay, what the unknowns are. And I think you can also quickly work out that B is oxidized because B is iron 2 hydroxide. Therefore, it's oxidized by oxygen in the air to form iron 3 hydroxide. And finally, the chemical equation for sodium hydroxide and ammonium chloride should be fairly straightforward. Now, for this question, you are not asked to write the state symbols. Okay, you are not asked to write the state symbols for part C, so don't need to write. However, if you really wanted to write, it's also not difficult, I think. Okay, so ammonium chloride and sodium hydroxide in these cases are aqueous. The sodium chloride is also aqueous because sodium chloride is a soluble salt. It dissolves in water. So these three are aqueous. Ammonia, gas. Water is a liquid. So these are the state symbols if you really wanted to write them in. Now, this is the chemical equation for the reaction between aqueous sodium hydroxide and ammonium chloride. But what if I wanted to write the ionic equation for the reaction? So you can see I'm training you as we do TYS, as we do the prelim papers, to write more and more ionic equations. So how do we write the ionic equations for this? Now, the whole logic is whatever is aqueous, we split up into the ions. And that's where the state symbols come in. The state symbols tell you whether to split up into ions or not. If it's aqueous, we split. So NaOH contains Na plus and OH minus. Ammonium chloride, ammonium, which is NH4 plus, Cl minus. Okay, so we have split up the sodium hydroxide and the ammonium chloride. Next, sodium chloride is also aqueous. So we will split up into Na plus and Cl minus. So the aqueous ones, we have all split up already. The remaining gases don't split. NH3 don't split. Liquid don't split. H2O. Now the whole purpose of splitting up is so that you can see which ions remain unchanged from the left to the right. So if you just look at whatever I've split up so far, what has remained the same? What has remained the same and unchanged? There are two ions which have remained the same. Which two ions are these? We can type in the chat. Okay, very good. Grace Lee's answer for everyone. Dave also. So Na plus remains the same. Whatever remains the same, cancel. Cl minus also the same, cancel. And I'm sure you'll agree with me, the rest have changed in some way. For example, at first it's OH minus, now it's H2O. At first it was NH4 plus, now it's NH3. So these have changed. So the ions that have changed, we will continue to write them in the ionic equation. So the final ionic equation is this. This is the final answer for the ionic equation. Okay, and this is how you deduce the ionic equation for this reaction, by splitting up into ions for the things which are aqueous. And after doing that, you see which ions have remained unchanged and the same from the left to the right. Now, these ions that remain unchanged, Na plus and Cl minus, they are known as spectator ions. They are spectator ions because they did not change during the reaction. They just sit down there and look at the reaction. They are spectators of the reaction. So the ionic equation will cancel away all the spectator ions so that you're only left with the ions which have changed. All right, and you notice the ionic equation must have state symbols. Okay, so the state symbols are important for ionic equations, even if they didn't specify. Okay. Okay, let's move on to question 6. Now, question 6 is about crude oil, and they tell you crude oil is a mixture of hydrocarbons and is separated by fractional distillation. I think you already knew this. Now, what do you understand by the term hydrocarbon? So I hope you know. Hydrocarbons are organic compounds which contain hydrogen and carbon atoms only. But what I wanted to go through is part B. Which fraction will burn in air with the most smoky flame? And explain your answer. What does most smoky flame mean? You have learned properties of each fraction. You have learned things like boiling point, viscosity, flammability. So this most smoky flame, which property is it related to? Okay, I think you can work it out. It's about burning. If it's about burning, clearly this is about flammability. So if it's the most smoky flame, what does it say about the flammability of this fraction? Is it high flammability or low flammability? Remember, high flammability means it burns very well. Low flammability means it doesn't burn very well. So most smoky flame means what? Burns well or doesn't burn well? So if you were to think about it, would you want a flame to be smoky? If a flame is smoky means what? Wow, it's producing lots of smoke, lots of soot. It's not burning well. If the flame is smoky, something is like, oh, not right, right? So it's low flammability. All right. So which fraction will have the lowest flammability in this case? So obviously, between A, B, C, D should be fraction D. Fraction D will be the lowest flammability. Why? Because it has the highest boiling point, meaning it has the largest number of carbon atoms, making it the least flammable. Remember, hydrocarbons, as the number of carbon atoms increases, the flammability decreases. So in this case, fraction D having the highest boiling point, that tells you that this has the largest number of carbon atoms, and therefore it is the least flammable. All right. So if it's the lowest flammability means it tends to undergo incomplete combustion, which of course produces CO, soot, and water. And this soot is what you see as smoke. So a smoky flame means there's a lot of incomplete combustion going on, and that is a sign that something has a very low flammability. Okay? Okay, so I shall go through the remainder of the questions a little bit quickly. So part C, I think I'll just leave it up to you to work out the equation for cracking. Okay, in particular, you will need to work out the final product is actually C4H8. Okay. Next, part D. All right, draw the structure of the monomer. So how do you do that? We do that by identifying the repeat unit. We identify the repeat unit by taking the 2 carbons in the main chain. Remember, the repeat unit always has 2 carbons in the center. These are just sides, side groups, if you like. So you basically close back, and form the double bond. So you have a carbon-carbon double bond in the monomer and the 4 side groups attached to the carbon atoms. So what is one chemical test to differentiate between the monomer and the polymer? So I've gone through this in class before. The monomer has a double bond between carbon. The polymer doesn't. So the best thing to do is to add aqueous bromine. By adding aqueous bromine, you can see which one is the monomer and which one is the polymer. The monomer decolorizes aqueous bromine from reddish brown to colorless. The aqueous bromine remains reddish brown when added to the polymer. Now, instead of saying no visible change, which is still okay, it might be better to say it remains reddish brown. Okay? So these are the answers for the questions. I believe we are moving on to section B after this. Yes. Okay. Okay, so ensure that you can do polymerization and can describe polymerization. So it's not just about drawing, it is also about differentiating between the monomer and polymer using aqueous bromine. You also need to be able to describe the process of addition polymerization, because you already know we have questions whereby we just ask you to describe the process. So you need to study organic chemistry thoroughly so that you know how to describe the processes. Okay? Now, so I think moving on to section B, I will skip question 7. I've written the answers in OneNote. Please go check the answers. All right. Now, question 8, again, first part I will skip because I've written the answers in OneNote, and this resembles some of the questions that we have already gone through together in class. All right. Now, let's just go to question 8, part D. Now, question 8, part D, it is a mole concept question. All right, where you are told that ethanol can be manufactured from the fermentation of glucose. So how do you find the maximum mass of ethanol that could be made from 36 grams of glucose? All right, so I think this is quite straightforward. It's a mole concept problem. All you needed to do was to figure out, okay, so 36 grams must be converted to moles. I do that by taking 36 grams divided by the MR of glucose. And that gives me 0.2 moles. All right. After finding number of moles of glucose, I use the mole ratio and work out that it's 0.4 moles of ethanol. Once I've used the mole ratio, worked out is 0.4 moles of ethanol, I just have to find the mass of ethanol, which is 0.4 times the MR of ethanol, which gives me 18.4 grams. All right, so this is not the difficulty. So the question now is, will we get 18.4 grams in reality? So based on mole concept, you have calculated that ethanol's mass obtained should be 18.4 grams. However, in reality, will we get exactly 18.4? Or will we get more than 18.4 or less than 18.4? What do you think? Can we type in the chat? Will we get more than 18.4? Exactly 18.4 or less than 18.4? Okay, so Jia says less. Okay, good. Who else? Others no response. Okay, less. Okay, so we all know that it must be less, right? Now, why is it less though? So this goes back to whatever we have learned under fermentation. So if we recall, for fermentation, we need glucose solution, 37 degrees Celsius temperature, and the absence of oxygen. Moreover, we have to add yeast. We know that the yield of ethanol is 15 to at most 20%. And this is because high concentrations of ethanol kills the yeast. So we will never ever reach 18.4 grams. Never. In fact, what is actually possible to get? What is actually possible? The actual mass is more like 20% times 18.4. The actual mass is probably 20% times 18.4, which is 3.68 grams. All right? Because I cannot exceed 20% of what I can achieve. In theory, my yield is 18.4, but in reality, the actual mass obtained is actually way less than 18.4. Okay? Next, how do we purify the ethanol? Which method will we use to purify the ethanol from the mixture? So the answer, of course, is the method used to purify ethanol is fractional distillation. All right, so I've said this before in class in our fermentation notes. I've also written it down. Fractional distillation is the method of separation to purify ethanol from the mixture. All right. Now this works because obviously the ethanol has different boiling point from the impurities. Okay, and final question for today. What is the main impurity in fermentation? What is actually the main impurity in the ethanol during the fermentation? So this is worth thinking about, right? You might think that the main impurity is yeast. Well, the answer is no, because you only added a very, very small amount of yeast powder. Yeast is a catalyst, it contains enzymes. You don't need so much enzyme, right? You might think it's glucose, but the reality is no, it's not glucose because you dissolve glucose in water. So the main impurity in the ethanol is actually water. And that's why fractional distillation works very, very well. All right. Okay, so ethanol boils at 78 degrees Celsius, water boils at 100 degrees Celsius. So it's quite clear. Ethanol has a different boiling point from water. Okay, and so that concludes question 8. Okay, I hope you have taken this down to ensure that you understand fermentation. Okay, so we still have question 9. But question 9, I've also written the answers down for you already. So you can just check the answers on your own in OneNote. All right. So if you have anything that you're unsure of, please feel free to ask and check from OneNote. Now, before we go, just give me 2 minutes. I'm so sorry. All right. I've written down just now. Okay, for those of you who joined late, under the contents library, under TYS, I have listed out all the questions, okay, for planning experiments that have come out since 2015 till 2022, including the salt prep questions. So you can quite clearly see every year there'll be a planning question in your theory paper. So far, the planning questions have mostly been about speed of reaction. However, there have been planning questions, as you can see, 2017, 2022, it was about speed of rusting. So to measure the speed of rusting, we measure the increase in the mass of the metal. Because when a metal corrodes or when a metal rusts, the mass actually increases. All right. Besides that, in 2020, we have also seen a question whereby we investigated the speed of oxidation of the alcohol. For this, we measure pH. Because the alcohol is oxidized to form the carboxylic acid, so the pH decreases. So can I please encourage everyone to revise these planning questions to ensure you know how to plan an experiment. Next, in terms of salt preparation, all right, you can see quite clearly. So far, we have tested excess solid plus acid, excess solid plus acid, excess solid plus acid a number of times. All right, titration has only appeared in 2019. Precipitation hasn't really appeared at all. In fact, last year's precipitation was as part of a mole concept question. All right. And you must also study the 2-step salt preparation in 2017. So if you are still lost as to what is the 2-step salt preparation like, please refer to my Sec 3 notes under salt prep. Right at the end, I've given you the answer, in fact. All right. how would you do a two-step combination salt prep? Okay, so please ensure you study all the notes thoroughly before Wednesday's exam. Okay, so that concludes my lesson here. All right, thank you so much.